Okay, students, I'm going to be giving a lecture on chemical reaction engineering, and the topic is packed bed reactor design, external resistance to mass transfer. Up to this, what we have learned is fluid flow passed over a single particle. But when you are talking about the packed bed reactor, the packed bed reactor is filled with multiple particles. So in that consideration, we have to consider the design part will be quite different than the single particles. Now, before going to this part, we must say that most of the reactions which happens in the industry, they are actually happens in the very high temperature, mainly the side reactions, so that the byproduct production will be less. Now, whenever we are talking about the side reactions, then we must say that the rate of reaction, that means the surface reaction, is very, very high, and the internal diffusion is also very, very fast. So, in that consideration, we can assume that the external mass transfer resistance will be high. That means the external diffusion rate will be nothing but the rate limiting step, and that will govern the overall whole reaction rate. Now, in this to achieve this in this section, we are trying to develop we are trying to design the packed bed reactor, the packed bed reactor length, and the weight of the catalyst. And before that, we are trying to derive the concentration profile in the packed bed. Now, to achieve this goal, we consider a reaction. You can see here the reaction is given. That reaction is happens in the packed bed reactor. That is A plus B gives you the C plus D. Now here the control reactant we consider as a A. So here you can see the packed bed is given will give multiple particles, and to develop the concentration profile we have to consider a fundamental volume. So that volume is nothing but here it considered that is the PZ is the segmental height where we derive the mole balance, we do the mole balance in that segmental volume. Now, try to develop the mole balance equation. So, to mole balance equation, it will be actually molar flow rate in minus molar flow rate out plus molar rate of generation and equals to accumulation. Rate of in minus rate of out plus generation equals to accumulation. Now, whenever we are trying to develop the mole balance, to develop the concentration profile, we have to consider that process is steady state process. Now, when the process is steady state process, we must consider that the accumulation term will be zero. So, this term will be zero. The molar rate of accumulation term will be zero. Now here the FAZ is molar flow rate of species A at Z, and FA at out it will be FAZ at Z plus delta Z. So that is in minus out plus generation. So generation is actually nothing but though it is called as a generation, but actually it is not a generation, it is decomposition of the rate of decomposition of A, and generation is with respect to product. So whatever the A is getting decomposed, that will be converted to the product. So RA double prime is the rate of decomposition of A, and that AC into delta Z. AC into delta Z actually, AC is actually nothing but the cross sectional area of the packed bed, and delta Z is the thickness of this segmental section. So this the volume of the segmental section will be nothing but AC into delta Z. So this is the volume of the segmental section, and this AC is external surface area of the catalyst particle per unit volume. So that will be external surface area meter square per unit volume meter cube into meter cube, that gives you meter square, and that rate is actually molar rate is moles per meter square into second. So meter square will be cancelled out. So that will be gives you the molar rate, moles per second. So that will be the term is comes from the molar rate of generation. So this is your mole balance. Now come to the convert it into the D form. So to convert it into the D form derivative form, so we have to divide the equation by AC into delta Z and take the delta Z tends to 0. So if you do these things, then what will come? That equation will come, that is minus 1 by AC d of f az dz plus r a double prime AC equals to 0. So this is the D form of the molar rate of equation, mole balance equation. Now come to the part. Now here our aim is to find out the concentration profile inside the packed bed reactor. So what you have to do, you have to convert that FAZ in terms of concentration and that RA in terms of concentration. So what is FAZ? FAZ is actually molar flow rate. FAZ is molar flow rate. So if we consider the molar flux is WAZ towards the Z direction, and if you multiply the cross-sectional area of the bed, so flux into area gives you the molar flow rate. So that is the molar flow rate FAZ AC into WAZ. Now come to the WAZ. What is WAZ? WAZ is actually molar flux. So here, as we consider the packed bed, there are several multiple particles are there. We have to consider two types of fluxes. One is diffusive flux, another one is convective. Now, diffusive flux happens due to the concentration, and convective flux happens due to the pressure gradient. So this JAZ is the diffusive flux and consider BAZ as convective flux. The JZ is happens normally if you go to the picture. So normally happens due to the concentration gradient. So initially here actually if you consider that CA concentration is very high and there the CA concentration is initially there is low CA concentration. So what will happen is the particles try to goes from higher concentration to lower concentration, but there is a separate blockage due to as the several multiple particles are packed inside the packed bed reactor. So diffusion is happens towards this direction, towards this direction, like this way, like this way. But diffusion rate will be very, very high due to the blockage of these particles as the particles are stagnant there. Now, if you think about the convective flux happens due to the fluid flow, due to the velocity of the flow. Now, and it happens due to the pressure gradient. Now, to achieve to flow the fluid from this side to this side, you have to give your you have to flow the fluid at a higher velocity, and that velocity should be greater than the superficial velocity. That means empty tower velocity. So the velocity should be greater than the superficial velocity. So when we consider that higher velocity, definitely we must say that the convective flux is much higher than the diffusive flux. The convective flux is happen in this direction, and the diffusive flux is happens in this direction. In this direction. So here, instead of considering these two flux, we just ignore the diffusive flux. So what will comes? The WAZ comes will only the WAZ will comes only PAZ. So WAZ equals to nothing but PAZ. So substitute the WAZ that WAZ as a PAZ. Okay. So here you can see here the WAZ PAZ, and that PAZ equals to nothing but U into CA. U into CA. So U is the superficial velocity and CA is the molar concentration. And W is actually what? Flux. Okay. Flux, flux that is here and that is flux means moles per meter square second. And here if you consider U is meter per second and this side is concentration is moles per meter cube. So here if you do this, that will come to actually moles per meter square second. Okay. Now substitute all the things in that mole balance equation. So FZ substitute that FAZ here in that mole balance equation, what we will get? Minus 1 by AC equals to D of WAZ into AC by DZ plus RA double prime AC equals to 0. So what is WAZ? We take WAZ as BAZ. So BAZ into AC by DZ R double prime AC equals to 0. Now, what is BAZ? Consider that is BAZ U into CA. So substitute all the things. So here you can see that AC will be cancelled out, and you will, as U is the constant superficial velocity, we consider that U is the constant superficial velocity. We must say that U U will be taken out from this derivative term, form. So U into dCA by dz plus RA double prime into dC equals to 0. So this is your one of the mole balance equations where considering the constant for constant superficial velocity. Now, now for steady state. Now again we are trying to replace the RA term, RA double prime in terms of concentration. RA double prime in terms of concentration. So here, what is RA double prime? RA double prime is actually nothing but the decomposition of A, reactant A, decomposition of the reactant A. Now, we must say that if you consider this is a single particle and this is a boundary layer thickness, now the concentration of the bulk gas phase is considered as a Ca, and that of the at the surface it is considered as a CAS. Now, whatever the species it comes from bulk gas phase to the surface, whatever the species that comes from bulk gas phase to the surface of the catalyst, so that is actually considered as a rate of diffusion rate of species A towards the earth direction. Rate of diffusion of A towards the earth direction, so that whatever the species that comes to the surface and the surface reaction rate is very very high. Initially, as I told you that due to the higher temperature, the surface reaction rate is very very high. So we must say that whatever the species A comes to the surface of the catalyst, they are quickly consumed. There will be no leftover areas there at the surface. So they are quickly consumed and converted to the product C and D. So in that scenario, we can say that is approximately 0. So here we consider that CAS is approximately 0. Before that, we must say that what is RA? RA is considered as a rate of diffusion, mass transfer rate. So what when we are talking about the mass transfer rate, there should be a concentration gradient and the mass transfer coefficient. So mass transfer coefficient and the concentration gradient gives you nothing but the diffusion rate. Ca minus Cas is the concentration gradient inside the boundary layer thickness. Now, so as the Ca is 0, we can substitute this in place of Ra, we can substitute Kc into Ca minus Cas. So here Kc into Ca minus Cas, and you can remove the negative sign. So negative sign will be removed, and the equation is comes reduced to this equation. We to dCA by dz plus Kc Ca minus Cas into Ac. Now as the Ca is 0, as the whatever the A's comes to the surface, they are quickly consumed. So we consider CAS is 0. So the equation get reduced to U into dCA by dz plus Kc into Ac dot Ca equals to 0. Now this is the reduction of the mole balance equations, and the equations comes in terms of concentration, velocity, superficial velocity, and the thickness of the and the length of the pipe. Let's say length of the pipe. So if you rearrange the equation will come as a dCA by Ca equals to minus Kc Ac U into dz And if you integrate the equation taking the boundary conditions, like at z equals to 0, it will be Ca will be Ca naught, that is initial reactant concentration, and at z equals to z, the reactant concentration is considered as a Ca. So if you put these two boundary conditions and do the integration of this equation, then you can get the concentration profile. So this will be your concentration profile inside the packed bed reactor, that is Ca by Ca naught equals exponential Qc in Ac uh, by U into J. So, at a constant superficial velocity, the concentration profile is a function of Kc, Ac, and U. So, you may say that as the length is increased from 0 to towards this direction, towards the Z direction, so the reactant species A that will be getting consumed and the product will getting increased. So the concentration of the Ca is gradually decreasing as the Z is increased from 0 to towards the Z direction. So thank you. Today to this next class will in that next class again we'll try to develop the length of the pad from this concentration profile. And today up to this. Thank you.